For this section, we are going to use what is referred to as Riemann sum to approximate the area under curves. So you'll see in this section that we're going to make these estimations just using shapes that we know. So we're like straight up doing geometry, base times height. We are calculating the area of these rectangles over a given interval from A to B. And in this unit, we'll be doing what we refer to as left-hand Riemann sums, right-hand Riemann sums, and midpoints. So let's get started and see what that looks like. You'll see here, we've got three different graphs, but we are calculating or approximating the area under the curve for all three. For this one, the R just means we want to use a right-hand Riemann sum to approximate that area. So what that looks like geometrically is we are going to look at each individual rectangle, but we are going to choose to have the height be the right hand of each respective rectangle. Here's what I mean. This is rectangle number 1. We're going to use the height to the right for this because both of those sides are different lengths. So we're going to use the height to the right. We're going to go to the second rectangle and use the height to the right. And we continue to do this until we get to our end, our B value. So you'll notice here that approximation is using a right-hand Riemann sum. You use the height to the right. Now the L, you guessed it, means you're using a left-hand approximation. So I'm still starting with that very first rectangle, but in this instance, I'm going to use the height to the left. That would be that height right there. So I'm going to use that as my corresponding height, and I'm going to keep repeating that process for my approximation for every rectangle. So you'll notice for the right hand, in case this is of interest to you, we use our B value, but we don't use A, since you're using all of the heights to the right. For the left hand, we use the A value, but you'll notice that B isn't included in this. Now this guy right here, this is our midpoint. So we're actually going to have to find the height of each respective midpoint and use that. Here's what I mean. I'm going to say that's the midpoint of that first rectangle. And we're not like guessing in this. We'll do an example where we'll see how it's put into play. But that's the midpoint of that first rectangle. So I'm going to use its corresponding height. Looks like that. And I'm going to repeat that process and find the height of every corresponding midpoint and use that to be the height of each rectangle. So it would look like this. And that would be our midpoint approximation. Before we do a specific example, I want us to just look at this particular graph, f of x. And we'll notice that in this situation, if we looked at our left-hand approximation, that looks to be an over approximation because when we take the areas of all of those rectangles, it's actually more than the area under that curve. But if we look at the right-hand approximation, well, the area of all of those rectangles is actually less than the actual area under that curve. So what we're going to determine now is the behavior of when our left versus our right is going to be an over or an under approximation. And it has to do with whether or not our function is increasing or decreasing. So what's on the screen right now are just examples of how a function could be sketched as either decreasing or increasing. So you'll notice here, those top two are supposed to be the same function. You'll notice it's decreasing, but it's concave up, whereas the bottom two are decreasing and it's concave down. Doesn't matter, as long as they are decreasing. You'll see if we use a left-hand approximation on a decreasing function, both of those turn out to be over approximations, whereas for the decreasing function, using a right-hand approximation, looking at these two, those are both under. So when my function is decreasing, my left is always an over approximation and my right is always an under approximation. The flip happens when it's an increasing function. So you'll see that right here. The two ways a function can increase is either concave up or concave down. In both scenarios, we identify that the left-hand approximation, if our function is increasing, is an under. Whereas with our right-hand approximation, if our function is an increasing function, our right is going to be an over approximation.
So let's break down how some of our Riemann sums are evaluated. Now, one thing to keep in mind is when you are asked to approximate an area under a curve using a left or a right or a midpoint Riemann sum, they will tell you with 3 subintervals, with 4 subintervals, or with n subintervals. That just means that those are the number of rectangles that we'll use. If we are working over an interval from A to B and all of our rectangles are evenly spaced, then the width of each rectangle is going to be B minus A divided by n, because we know this interval right here, is B minus A. And if they're asking us to use 2 rectangles, well, the width of each one would be B minus A divided by 2. 5 rectangles would be B minus A divided by 5. N rectangles would be B minus A divided by n. This is referred to as delta x. Delta x is the width of each rectangle, given that they are all evenly spaced. They're not always that way. Next, let's see how this looks if I were using a right Riemann sum. So instead of v, I'm going to refer to this as a function f of x. If I'm using a right-hand Riemann sum, a sub 0 would be referred to as my x sub 0th term, and b would be my x sub nth term. With a right-hand Riemann sum, we use the height to the right. So here, if we're thinking in terms of our Riemann sum, it would look like this. Base times height. My delta x is the base, and it's actually the same base if they're all evenly spaced, and then my height is just f of x sub I. So if we were using a right-hand Riemann sum to find this approximation, you'll notice that my first rectangle would be base times height. And that would be the area of the first rectangle that I just shaded. And the second rectangle would look like that, base times height. And we keep going until we get to the very last rectangle. And if it's a right Riemann sum, we would use the f of b, the x sub nth term. Now you'll notice if they're all evenly spaced, we can factor out the delta x and have that be our equation. You'll notice the same idea works with the left Riemann sum. N rectangles would give us a delta x of b minus a over n. But now, if I'm using the height to the left, my first rectangle would be delta x times my f of x sub 0, my f of a term. And if they're all evenly spaced, I'm going to factor out that delta x, and we get the same formula, except we start at a, and then we would end at our second to last, our n minus 1th x value. Let's look at this example. We're asked to find a right Riemann sum with 4 equal subdivisions to approximate the area under the curve of that quadratic from x equals 1 to 9. So let's knock off a couple of pieces of information that we know. For starters, we know what our delta x is. If they're equally spaced, we know b minus a over n is 9 minus 1 over, and then n in this number of rectangles is 4. So we know our delta x is 2. Next, let's look at just a visual of this. So from 1 to 9, we know that we're going to have 4 rectangles, all of which are going to have a width of 2. So here's my rough sketch, and I know since each width is 2, I know what those corresponding coordinates are on my x-axis. 1, 3, 5, 7, and 9. Great. So now comes the right Riemann sum piece. If I'm using a right Riemann sum for the first rectangle, I'm using f of 3 as the corresponding height. So we can write our summation with our delta x outside of the parentheses, and within it, f of 3 plus f of 5 plus f of 7 plus f of 9. Since all of those values are the heights of our rectangle, and we know that 2 is the base. So next, I would have my calculator ready, and I would put this equation into my y1 and evaluate what y1 of 3, y1 of 5, 7, and 9 are. And when we calculate it, we end up with this, which later gives us a total of 180. Let's look at this example where our widths are not equally spaced. So here we are given a tank has a height of 10 feet, and the areas, the A of H, are cross sections of the tank at certain heights H. So we have A of H, and that is our area, and that's in square feet, and H is in feet. So we know A to be continuous and strictly decreasing as our H gets bigger. So here we've got this table of values. We're asked to use a left Riemann sum with 3 subintervals to approximate the volume of the tank. And we all know volume is just area times height. For example, if it's a rectangular prism, it would be length times width times height. So the first thing that we want to do here is let's identify what the widths are because they vary. So the width of that first rectangle from 0 to 2 is 2. The width of the second rectangle from 2 to 5 is 3. And the width of the third is 5. Now if I'm using a left Riemann sum, for the first rectangle, I'm going to use the height of 50.3. If you need, draw a quick sketch. And then you can see that the first height would be the height to the left of 50.3. But then it just keeps going. So let's look. The first rectangle would be base 2 times height, 50.3. Plus, my second rectangle has a base of 3 and a height of 14.4. And the third has a base of 5 and a height of 6.5. And we can see it even if we sketched it like so. This cleans up to give us 176.3, and since we were taking square feet times feet, well, that's cubic feet. So the next question asks, is this an over or an under approximation of the volume? This is where we identify that A is decreasing, and since we used a left Riemann sum, we know that our approximation was an over approximation since a left-hand Riemann sum was used and our function a is strictly decreasing.